So if HS is the analog filter response, and we have to get a digital filter out of it, then we need to find out HZ. We need to find out HZ because HZ is transfer function for the digital filter, digital system. So what will be the transformation? According to impulse invariance method, we have to replace S को किससे replace करना है? We have to replace it by e raised to power minus t z raised to power minus 1. Okay, z raised to power minus 1. Most of the time, if t is not given, we take it to be 1 second. If t is not mentioned, generally we take it to be 1. So what will be this? This will be simply 1 by 1 minus e raised to power minus t z raised to power minus 1 minus 1 upon 1 minus e raised to power minus 2t z raised to power minus 1. Okay, so by using this transformation with the pole is at pi, we can get HZ to be like this, and when we simplify it, we will get it to be z raised to power minus 1 e raised to power t minus e raised to power minus 2t. Okay, 1 minus e raised to power minus t plus e raised to power minus 2t. This expression for z, and when we assume sampling to be 1, if sampling is assumed to be of 1 second, that is sampling frequency is 1 Hertz, then it will reduce to 0.2326 z raised to power minus 1 minus 0.503 z minus 1 plus 0.0498 z raised to power minus 2. Okay, so moment we get HZ, we got the digital filter, IAR digital filter. So this is how impulse invariance IAR digital filter could be designed, where we have to perform this transformation. Okay, suppose we have an HZ and we want to implement it. मतलब कि HZ we have designed HZ, but how to implement it? So we have to learn it from the S domain. S domain में क्या करते थे? So एनालॉग डोमेन यानी कि S डोमेन में एनालॉग फिल्टर के लिए we generally use adders. We have adders, then we have multipliers, and we generally have integrators. So these are the blocks which are used to realize a analog system. These are the three components which are used to analyze a system in the analog domain. One is adder, then there is a multiplier, and there is an integrator. Okay, these are the three basic components which are used to realize a system in the continuous time domain. Okay. Now adder and multiplier are common. In the digital domain also we can have an adder and we can have a multiplier. But what about the integrator? How to realize an integrator in the digital domain, in the discrete time domain? Okay, because integrator is something which is used to perform on the continuous time domain. So what happens in the digital domain? Let us suppose y analog t is the output for an integrator when input is x analog t dt. Okay, let us suppose this is the output of an integrator, and let us suppose at the instant nt, yani n times the sampling period t, we have what will be the output? Output will be, can be written as y n minus 1 t plus integration of n minus 1 t nt. Okay, and x a t dt. Okay, so this integration can be, because if we have to find out x and t, matlab x a at the instant nt, then it can be written as n minus 1 t and integration from n minus 1 to nt. Okay, this equation this is the exact equation. Now it can be approximated to y a and t n minus 1 t plus, and what is integration? Integration is basically an area, so it can be approximated to area of this nt plus xa and minus 1 t bracket close into t. Okay, so extreme points of xa into the base is t, because n minus t, when it is minus n minus nt minus this thing will be t. So this integration can be approximated to this expression. Transform this equation to our discrete time quantized version equation, then it could be written as yn, y at the instant, yani ki y output yn is equal to yn minus 1 plus t by 2 x n plus x n minus 1. So then in the discrete time domain, this equation can be written like this, and we get the difference equation which relates input and output of the digital version of the analog integrator. Basically, this equation gives you the digital version of the analog integrator. This equation gives you digital version of the digital version of analog integrator. So we can call this as analog integration. We can call it digital integrator. Okay. So when we transform it in the z domain, we will get yz. अगर इसका z domain में transfer करेंगे इस equation का, and z minus 1 yz plus t by 2 xz plus z minus 1 z raised to power minus 1 xz and it can be written as yz by xz can be written as t by 2 1 plus z minus 1 divided by 1 minus z minus 1. Okay. And because what is integrator in n domain? S domain में integration is 1 by s. Integration is performed by 1 by s transformation. So this will be approximated to 1 by s. This means this will correspond to 1 by s. So that we have s. If we compare these two, so s will be 2 by s will be not equal to z, because both cannot be equated, but it can transform to 2 by t 1 minus z raised to power minus 1 and 1 plus z raised to power minus 1, like this. So S transforms to Z domain like this. S transform to Z domain like this, and this transformation is called bilinear transformation. So any given analog signal, any given analog filter can be converted to a digital filter under the transformation S equal to 2 by t 1 minus z raised to power minus 1 plus z raised to power minus 1, and this transformation is performed with the good approximation to digital filter. That is, basically summation and multipliers are the same in the digital and analog domain, but it is only the integrator that need to be replaced, and that is done by this transformation, S changing to 2 by t